You and four friends are standing at a food truck. Call yourselves A, B, C, D, and E. The owner says, free sandwiches for any two of you. In how many ways can you pick which to get fed? Now a twist. The owner has two different sandwiches, one spicy, one mild, and you must decide who gets which. Same two people, but now the roles are different. The people are identical in both stories. The only thing that changed is whether who gets which matters. That single question, does order matter, is the whole difference between combinations and permutations. Everything in counting grows out of one simple rule. If a task happens in steps, you multiply the choices at each step. Say you own 3 shirts and 2 pairs of trousers. Picture 2 slots, one for the shirt, one for the trousers. The shirt slot has 3 choices. The trouser slot has 2. 3 times 2 is 6 complete outfits. The power really shows when the slots repeat. Take a short quiz with 5 questions, each having 4 options. That's 5 slots, 4 choices in every one. 4 multiplied by itself. 5 times is 4 to the 5th. 1024 different answer sheets from just 5 little questions. Before permutations, we need one small piece of shorthand, the factorial. N factorial just means multiply every whole number from n all the way down to 1. So 4 factorial is 4 times 3 times 2 times 1, 24. And 5 factorial climbs to 120. They grow ferociously fast. One convention looks strange at first. 0 factorial is defined to be 1, not 0. There is exactly one way to arrange nothing, do nothing, and as you'll see, that one keeps every later formula honest. Now permutations. When order matters, we count ordered arrangements. Suppose you have n distinct objects and you want to line up r of them in a row. Think of our slots. The first slot can take any of the n objects, but the second slot has one fewer to pick from. You already used one. The third has n minus 2, and so on. Multiply those shrinking choices together, and you get npr. Written with factorials, it's n factorial divided by n minus r factorial. Make it concrete. 3 friends, A, B, C, and 2 labeled chairs. 3p2 is 3 factorial over 1 factorial, which is 6. And here are all 6, spelled out. A to B and B to A are counted separately, because sitting A on the left is a genuinely different arrangement from sitting B on the left. Order matters. Combinations answer the other question. When order does not matter, and you only care which objects you selected, not how they're arranged. Here's the clean link. To build an ordered arrangement, you can do it in 2 steps. First, choose which are objects. That's n choose our ways. Then arrange those are in order, which is our factorial ways. So the ordered count, npr, is the unordered count times our factorial. Turn that around, and n choose r is simply npr divided by our factorial. Written fully, n choose r is n factorial over our factorial times n minus r factorial. That our factorial on the bottom is the machine that erases order. Back to our 3 friends. But now the 2 sandwiches are identical, so it's pure selection. 3 choose 2 is 3 factorial over 2 factorial, 1 factorial, which is 3. Just 3 groups, a 2b, a 2c, b to c. Notice A to B and B to A have merged into one. Ordering the same to people no longer counts as new. Exactly what dividing by our factorial did. Let's checkpoint with 4 choose 2, done 2 different ways. Straight from the formula. 4 factorial over 2 factorial, 2 factorial, 254 over 4 is 6. Or through permutations, 4p2 is 12 ordered pairs, divide by 2 factorial to drop the ordering, and again you land on 6. 2 roads, same answer, always reassuring. 3 tiny facts fall out for free and save real time. There's exactly one way to choose nobody. So n choose 0 is 1. And this is precisely why 0 factorial had to be 1. Likewise, one way to choose everybody. So n choose n is also one. And the prettiest? Choosing r to keep is the same as choosing n minus r to leave behind. So n choose r equals n choose n minus r. The counts mirror each other. That mirror is a genuine shortcut. To find 10 choose 8, don't grind the big factorials, flip it to 10 choose 2, which is 10 times 9 over 2, 45. Far less work. One more essential case. Arranging objects when some are identical. Take the word level. 5 letters. But the two ls are indistinguishable. And so are the two es. If every letter were unique, there would be 5 factorial 120 arrangements. But swapping the two identical ls produces no new word. And the same for the es. So we've counted each real arrangement too many times. The fix is to divide out those invisible swaps. Divide by 2 factorial for the ls and 2 factorial for the es. 120 over 4 is 30 genuinely distinct arrangements. Time for a fuller problem. A class has 10 students. We want a team of 3. And then within that team, a captain and a vice captain. 2 different roles. How many such teams withdrawals are there? I'll solve it 2 ways, and they must agree. Method 1. Pick the team first, roles later. Choosing 3 from 10, order free, is 10 choose 3. That's 120 possible teams. Inside each team, pick the captain, 3 ways. Then the vice captain from the 2 left, 2 ways. 6 role assignments per team. Multiply. 120 teams times 6 role choices gives 720. Method 2, the other way around. Pick the captain and vice captain first. An ordered pair, so 10p2, which is 90. Then the third, roleless member comes from the remaining 8 ways. 90 times 8 is, once again, 720. Both methods agree, so we can trust it. Here's how counting feeds straight into probability. A box holds 7 red balls and 5 blue, 12 in all. You draw 3 without looking. What's the chance all 3 are red? Order of drawing doesn't matter. So we count selections with combinations. The total number of 3-ball selections is 12 choose 3. The favorable selections are the ones with 3 reds, chosen from the 7 reds, 7 choose 3, which is 35. Probability is favorable over total, 35 over 220. Cancel a common factor of 5 and it tidies to 7 over 44, about 16%. Your turn, and this one is deliberately two-phased. You have 6 different books. Part A. Arrange 3 of them in a row on a shelf. Part B. Simply choose 3 of them to keep. Pause here and decide for each part whether order matters before you compute. I'll wait. Part A puts books in a row, so order absolutely matters. That's a permutation. 6p3 is 6 times 5 times 4, 120 ways. Part B only cares which 3 you keep, not any arrangement, so it's a combination. 6 choose 3 divides that same 120 by 3 factorial, giving 20. Same objects, but order collapses 6 arrangements into each single group. If you split those two cleanly, you've truly got it. Trap 1, and the biggest. Never start computing before you've answered. Does order matter? Yes means permutations, or the slot method. No means combinations. Decide first, always. Trap 2. Forgetting to divide by our factorial. That division is the only thing collapsing all the internal orderings into one unordered group. Drop it, and you've secretly counted permutations. Trap 3. Using n-chooser when repetition is allowed. Combinations assume each object is used at most once. If digits in a code can repeat, go back to slots and powers, not choose. Trap 4. Ignoring identical items. With repeats, plain n factorial overcounts. Divide by the factorial of each repetition count. That's what saved us on level. Let's lock it all in. Everything begins with the multiplication rule. Choices in sequence multiply. When order matters, you want permutations. NPR is n factorial over n minus r factorial. When order doesn't, you want combinations. N choose or divides, that by r factorial to erase the ordering. And when objects repeat, divide n factorial by the factorial of each repetition count. In any new problem, ask first whether order matters. Watch for repeats. Then pick the formula. And most probability questions quietly become counting.